Welcome everyone in the Levitate webinar on road safety impacts. I see that we are more than 60 participants as of now, so I suggest Andrew to start the webinar.
Thanks very much, Balázs, and a very good afternoon to everyone, and welcome to this Levitate webinar. Thank you very much for joining us. My name is Andrew Morris, and I'm joined by several other colleagues from the Levitate project who will introduce themselves as we progress throughout the webinar session. First of all, I just need to remind everyone that this webinar is being recorded and we'll use it for dissemination purposes in the project. So if you're not in agreement with this recording for any reason, we respectfully request that you leave the webinar now. Secondly, if you have questions about the project or any of the presentations, please use the Q&A function at the top of the spacebar. Don't use the chat. If you could use that for clarification on the project, then we can differentiate between the two as to what are questions and points for clarification. So in the webinar today, we're focusing on road safety impacts of connected and automated transport systems. But first of all, I'm going to start by giving you a brief introduction to the Levitate project so that you can understand the overall aims and objectives of what we're trying to achieve within Levitate. So Levitate stands for societal level impacts of connected and automated vehicles. And the intention is that the project will build tools to help European cities, regions and national governments to prepare for future with increasing levels of automated vehicles in passenger cars, urban transport and urban logistics. The project funding is 6.4 million provided by the European Commission in the Horizon 2020 work programme. And the project, which is led by Loughborough University, brings together 12 partners from 10 countries, including renowned research institutes, local authorities, and other global partners. It's a 3-year project, and it started in December 2018. So I briefly touched on the partnership before. We have 12 partners in the project, and the partners address a combination of technical, stakeholder, and implementation challenges required for conducting the necessary research and preparation of a policy support tool. The partnership is also assembled in order to combine all of the necessary competences and expertise in order to carry out the technology evaluations through data analysis and microsimulation modelling, and to ensure a successful dissemination and exploitation of the project results. And then ultimately, the partnership demonstrates capability to successfully launch the policy support tool to be used by a range of stakeholders, including local and national roads authorities and other policymakers. Therefore, we've got a good blend of research institutes, universities, software and simulation experts, and road authorities within the project. The reason we're conducting this project is that overall there are high expectations and much optimism about what connected and autonomous transport systems might deliver in terms of safety, mobility, environment and societal benefits. But as yet, there's no standard means to predict what's really likely to happen and whether all of the predicted benefits are likely to eventuate, or whether there may be issues associated with the introduction of automated transport systems that we've not yet realised or anticipated. Also, maybe less obviously, we need to consider whether the potential benefits that we might predict in one particular parameter do not mean that there's a detrimental impact on another domain. So we need to consider all of the likely benefits and disbenefits collectively. And this sort of analysis is a little bit more complex than you might imagine, but it's no less important or no less necessary. So the overall aim of Levitate can be described as building the tools that will help the European cities and other cities for that matter, regions and national governments prepare for a future with what is predicted to be an increasing level of automation in passenger vehicles and other urban transport services and urban logistics. We will eventually develop an impact assessment framework which will be available to policymakers so that they'll be able to manage the introduction of automated transport to maximum effect. And this in turn will allow technology to be harnessed in order to achieve societal objectives. In order to achieve its objectives, Levitate is establishing a number of impact assessment methods. And the intention is that we'll establish how these can be applied across a range of future possible scenarios once automated vehicles become a reality, based on stakeholder inputs, quantification of impact dimensions and indicators, and the development of microsimulation models. We are then exploiting these methods to examine what might happen within each possible scenario based on modeling and microsimulation. So, for example, we might want to consider how driverless cars will impact on parking provisions within inner city areas. We might want to determine what the likely traffic flow into city centres might be if we decided to provide dedicated lanes for driverless cars. So once we've looked at a broad range of use cases and sub-use cases, we intend to bring all of the individual analyses together through the establishment of a policy support tool. And essentially, the policy support tool will be available to the city authorities and policymakers to assess the impact of a particular scenario. For example, congestion, based on changes that are likely to take place as automation becomes more prevalent. Hopefully, this will allow policymakers to study, for example, safety and crash rates and how they might change on different roadways if the composition of the vehicle fleet changes as a result of changes in the uptake of autonomous vehicles. And of course, safety is the main theme of today's webinar. And then once the policy support tool is completed, it will be available for general usage, and the project will thus engage in focused dissemination activities designed to inform stakeholders of the availability of the policy support tool. And with that, I'd like to hand over to my colleague, Wendy Wyemars, to talk more specifically about the impacts that we are examining within the Levitate project.
Yes, thanks a lot, Andrew. Could you go to the next slide, please? My name is Wendy Wyemars, and I'm a senior researcher at SWOF Institute for Road Safety Research in the Netherlands, and I coordinate the road safety work within Levitate. Before we discuss our results with you, I would like to start with a poll. So, Balázs, could you please start the poll? Yes. Do you see the question? The question is, to what extent do you expect road safety to be improved by developments related to cats? Could you please submit your answer to this question? I hope you can see the poll.
Yes, they can see it. I already see the answers arriving. Now 40 people answered from 72. Okay. So I encourage you to cast your vote.
I'm really curious about the results of this poll.
Now 50 people answered. Okay, there are more than 80% voted, so I'm going to end the polling and I'm going to show the results.
That's perfect. Thanks a lot.
And here is it.
So I see that most people voted that they expect a considerable improvement in road safety, but they don't expect that all serious crashes can be prevented. So let's discuss the results that we analyzed within Levitate and see whether it's related or it's similar to the expectations of the audience. So I'm going to close the poll, and Andrew, could you please go to the next slide? Yes, thanks a lot. So road safety impacts within Levitate are estimated by following a two-step approach. First of all, we determined in which ways the road safety is impacted by developments related to connected and automated transport systems. And as a second step, we try to quantify the impacts as far as possible within the project. And we analyzed in which ways road safety was impacted by doing a literature review and by discussing potential impacts with stakeholders. And the quantification of impacts is done by combining various approaches, which will be discussed in more detail during this webinar. So next slide, please. And we analyzed road safety impacts for, first of all, for increasing penetration levels of connected and automated vehicles that we call the baseline scenario. And as a second step, we looked at various sub-use cases, and the sub-use cases are related to three main use cases that were already mentioned by Andrew as well. Those are the passenger vehicles, the urban transport, which is public transport, and freight transport. And within each use case, we identified various sub-use cases that were discussed in more detail. Today, in the webinar of today, we focus on the impacts of the baseline scenario, so the impacts of the increasing penetration levels of CAFs. So next slide, please. So the program for the remainder of this webinar. First of all, Rins de Zwart will tell you something about the road safety impacts of CATs that can be expected. And then we will focus on the quantification of impacts within Levitate. First of all, the approach is briefly introduced by Rins again. And then Amna Chowdhury will say something about the estimation of impacts using microsimulation. Then Andreas Hula will say something about the estimation of impacts on vulnerable road users. And I will end with some closing remarks. And after the first part, the discussion of the road safety impacts that can be expected, there is some time to ask for your feedback in the chat. So let's continue with Rins. Can I give the floor to you? Could you share your screen, please?
Yes, definitely. Good afternoon, everybody. I'm a colleague of Wendy's, also at the Institute of Road Safety Research, SWOF. Let me share my screen. Is it working? I think so. I will talk a little bit about what road safety impacts we foresee within the Levitate project. First of all, let me explain. We have two main types of impacts we expect. The primary impacts, which are a direct result of the automation technology, the replacement of the human driver with the automation, and secondary impacts, which are a reaction to those primary impacts, a response of the environment, the society as a whole, basically, to the automation. I will first discuss the primary impacts and then the secondary impacts. The first primary impact I would like to discuss is the removal or reduction of human driver errors. Fully automated vehicles do not exhibit any human errors, such as distraction or fatigue. An automated system has no way to be distracted or to become fatigued. It always works the same way. It also exhibits improved reaction time. It's able to react quicker than a human can to the changing situations on the road. And it will always strictly adhere to the traffic rules. A next effect or an impact is the transitionary effects or operator error. The moment where we are now or close to is when vehicles are able to automatically drive for shorter periods of time, but there is a moment when the human driver has to drive as well. The switching between human driver and automated system poses a risk. The interaction there is not always smooth. The takeover situations are usually sudden. The lack of situational awareness just after a takeover request, especially a critical one, poses a risk. Mode confusion is a slightly less pronounced version of this. When a vehicle is capable of self-driving, but not currently self-driving, the human driver might still expect the vehicle to drive itself. The uncertainties about whether the vehicle is self-driving at the moment or in which way it is self-driving pose another risk. And of course, there is the potential for sabotaging or testing the limits of current systems. And this is already something we can see at the moment. People trying to get their current non-self-driving vehicles to drive themselves for as long as possible, move out of the driver chair, take their hands off the wheel as long as possible. In addition to this, we foresee some impacts relating to system security and system failure. And the hardware and software design currently is not tested on a national or international level. This poses risks, especially with updates that are just on the air. So there's no way to check what is in this update that changes the driving behavior of the vehicle potentially. And in addition to this, there's of course the cyber risks. It might be possible to manipulate the software of the vehicles, especially connected vehicles are at risk of outside manipulation. And there is again a need for rigorous testing to ensure that the systems are safe, that no update changes the behavior in any significant way or introduces new risks or ways for the system to make a mistake. As for the secondary impacts, these are indirect impacts, and the most pronounced one is behavioral adaptation. This is when a vehicle is an automated vehicle and we see that the behavior of the people outside of the vehicle changes. We see the copying of connected and automated vehicle behavior, which could result in unsafe situations. These vehicles are expected to drive closer together, which is possible due to their lower reaction times. These are not possible reaction times for human drivers. However, it's already been observed that when driving next to platoons, human drivers will also copy this smaller headway, drive closer together without the ability to react at the same speed as the automated vehicles. In addition to this, there's a frustration towards the CAFs. Strict rule adherence might cause frustrated behavior. Driving behind an automated vehicle, strictly sticking to the speed limit, causes frustrated behavior, as we've seen already in some studies with intelligent speed assistance. This will only become worse when there are more vehicles. The potential for conflicts between crossing pedestrians or cyclists and self-driving vehicles is an extra potential for risks. Challenging a vehicle that you know to be on the defensive side of driving to quickly cross the road, this might be behavior that will become more possible or will become more exposed. And then there are the mobility changes or the changes in mobility behavior. Due to the CAF introduction, it is very likely that there will be changes in the travel choices. There will be a higher availability of motorized transport. It will be available for more people than it is now. Younger people that don't have a driver license, older people that lost their driver license, or whoever else that is not currently able to use the motorized transport. For those people that do already use it, there's the ability to utilize the travel time differently. You could work, relax during the travel, which is currently not possible. And there's also the potential for unattended use of smaller roads as shortcuts. Connected vehicles might communicate between each other, and they might choose to drive through a neighborhood in order to drive around congested roads. There's the potential for changes in modal split. As these vehicles become more available, it's likely that there will become a move away from active modes of travel towards these connected and automated vehicles. And these effects are strongly dependent on availability of these vehicles, how they are implemented, and other methods or measures related to the different modes of transport. And finally, the potential for empty vehicle kilometer travel. This is the potential where vehicles can drive you to work and then return home, where somebody else can use them. They can drive around the city in order to avoid parking fees. And there are multiple ways in which a vehicle can drive itself around in order to have different uses. This will drastically increase the amount of travel we see. And this is something that should either be regulated or we have to find out how much potential there is here. In general, when there is an increase in distance traveled, there is an increase in exposure, and if nothing else changes, this will result in an increase in conflicts. Finally, the infrastructural measures. Current automated vehicles rely on clearly visible road markings, on clearly visible road signs, and if this continues to be the case, human drivers will also benefit from these improved road standards. And the changes in public space, as already mentioned by Andrew, the potential to remove on-street parking due to self-parking abilities, or the removal of extra lanes due to the ability to drive close together, potential safety risks due to parked cars are removed, or there's the other ways in which public space can be used that is currently not available due to the need to have this extra space there. That is it for the impacts. I'm not sure I can start the poll or the Q&A session.
No, there is no poll. Thanks a lot, Rens, for this presentation. Can you hear me?
Yeah, I can.
Okay, perfect. Rens presented different types of impacts that were distinguished within Levitate. We hope we have covered all impacts, but of course, it's always possible that we forgot about an impact. So if you have any suggestions for additional impacts, please send us your suggestions in the chat. I also saw there are quite a lot of questions already coming in, and we try to answer them as soon as possible. So if I don't see anything in the chat yet, you can, during the remainder of this webinar, please insert your suggestions. And if I don't see any suggestions at this moment, then please, Rens, continue with the second part of the presentation, which is about the quantification within Levitate.
Of course. Let me see if the second part, of course, is about the quantification. Not everything I just mentioned or is mentioned in the Q&A or the chat can be quantified. A number of them are on this slide. The impact of human errors, distractions, and errors of judgment is not something we quantify within a Levitate project. The same goes for system failure. These are very difficult to simulate or to do on a wider scale. And the transitional effects and the mode confusion, the takeover requests are outside of the Levitate scope. We focus on a more longer term, and this is a more shorter term and a small amount of time that this will be the case. The behavioral adaptation of the other drivers, which will copy the behavior, is something we study in an additional driving simulator study, and is not done with the methods we will discuss in a moment. All the other impacts are quantified within the project. And for this, we use three main methods. Indirect impacts will not be discussed in this webinar. These are the modal split or the increase in travel. Vulnerable road users will be talked about by Andreas. And microsimulation, Anna will discuss this right after this slide. I think that's the introduction.
Thanks a lot, Rens. In the meantime, I see there is a question about your first presentation.
Yes.
The question is, how about strict adherence from CAS limiting the ability to avoid accidents? Could you say something about that, Rens?
I'm not sure I understand the question. They're limiting or their adherence to the speed limit, or restricting their ability to avoid an accident. This is not something we have talked about in this slide. It's actually a very good point. I'm assuming you mean, for instance, speeding away from a vehicle coming from the rear in order to avoid a rear end collision. This is not something we quantify at the moment. I don't think this is captured in the microsimulation, but then I would have to rely on Anna for more information. I don't know if we should include this at the moment. I don't foresee this being a huge impact compared to the other ones, but it's definitely something we should look into. Did I interpret your question right? Are you talking about the ability to dodge an incident, basically? Okay.
Yes, it's mentioned that that you interpreted it correctly. So thanks a lot. I see also a comment in the chat. When talking about impacts and human errors, it was not clear what your conclusions are regarding the human errors being replaced by computer errors, human confusion and system confusion.
Yeah, good question.
Yes.
We assume there will be moments when the system cannot recognize a certain situation, but this is very difficult to capture. So for the Levitate project, we assume the system will always be able to function, a level 5 system basically. We do note that this will of course not be the case. There will always be equipment failure, software failure. But this is already the case for current vehicles. Brakes can fail, acceleration pedals can fail. So this is something that's just too difficult to quantify. Relating the human errors versus the computer errors, the human errors are in a much higher order of magnitude than those of the automation system. So even though there will be system failure and cyber risks, this will, compared to the reduction in human errors, be negligible.
Yeah, just to add on that, there, as Rins mentioned, there will be system failures, and there are also issues, for example, with cybersecurity. But at the moment, it's not possible to quantify those risks, as they also depend on how, for example, on how exactly the CAFs will be programmed, and a lot of policy decisions as well. So those are not included in the quantification of impacts.
No.
I would like to continue with the next presentation. I would like to ask Amna to share her screen and to start the presentation.
Sure. Just a second. I hope you are able to see my screen.
Yes, we see your screen. Thank you.
Let me bring it to the presentation. Hi, everyone. My name is Amna Chaudhry, and I'm working as a research associate on Levitate project at Loughborough University. I will be talking about methods for estimating road safety impacts of connected and automated vehicles using microsimulation techniques. And I will also present some preliminary results from our test network. So let's begin with the basic question of how can we estimate safety impacts of CAFs when there is no real world data available? Well, of course, there isn't any substitute of real world data. However, it can be quite useful if we are able to model CAFs behaviors in our road network and be able to analyze various types of impacts, such as traffic, safety, and environment, by including through the intervention of CAFs. So in this context, traffic microsimulation techniques provide quite reasonable capability for modeling CAFs, for modeling behaviors of different types of vehicles and simulating them in the actual road network. And these techniques have also been used in recent research. And so by enabling users to model behaviors of different vehicles, one can analyze various types of impacts due to CAFs in the road network. Regarding safety impacts through microsimulation, a surrogate safety measure can be used from microsimulation output, that is traffic conflicts, which is basically an incident involving two or more road users where action of one road user causes the other road user to take evasive action for avoiding collision. And the primary assumption for using traffic conflicts is that the same factors which impact collision rates would also impact traffic conflicts. Within Levitate, we are using Aimson microsimulation for simulating CAFs and are varying from 0 to 100%. And also we have considered both passenger and freight vehicles in our freight composition, where automation of freight vehicles has also been considered. With regard to cabs characteristics, we have used two types of cabs in our simulation models: first generation cab and second generation cab, which basically differ from each other on the basis of their sensing and cognitive ability, decision making, driver characteristics, and anticipation of incidents, for example. So the idea behind this is that technology will advance and improve with time, as can be seen in various other technological systems. So the second generation cabs will have improved sensing and cognitive ability, and have enhanced, will be able to execute maneuvers in less time as compared to human-driven and first generation vehicles. For modeling cabs' behaviors in microsimulation, these are the key parameters that need to be defined within the model. And so primarily, they are needed to define vehicles' car following behavior, acceleration, deceleration characteristics, lane changing and overtaking behavior, behavior approaching a signalized intersection, behavior at unsignalized intersection with respect to gap acceptance, and connectivity related factors. So let's talk about surrogate safety measure, that is traffic conflict. From microsimulation, we are able to identify three major types of conflicts depending on the conflict angle, including rear end conflicts, lane change conflicts, and crossing conflicts. And this demonstration explains that what is the range of angle within which the type of conflict varies depending on the conflict angle. And also for identifying events as conflict, it is important to define time to collision value in the model, which is basically the time which starts when the following vehicle takes evasive action to the time when both following and lead vehicle would collide had they not changed their speeds. So the threshold value for time to collision needs to be defined for identifying events as conflicts through microsimulation. This shows the process for estimating conflicts from microsimulation and microsimulation output. So in our case, we have used Ames in microsimulation. So vehicle trajectories are generated from microsimulation, which are then used in FHWA's surrogate safety assessment model. This model has its default value for time to collision and post-encroachment time. So first we generate traffic conflicts on the basis of these values, and then we post-processed them by defining our own TTC thresholds, which are based on literature findings, including 1.5 second for human-driven vehicles, 1 second for first generation cab, and 0.5 second for second generation cab. We also identify vehicle types from trajectories to be able to estimate conflicts involving different vehicle types. And after that, the conflicts were converted to crashes by using a proposed method by Andrew Tarko. The reference has been provided at the end. This is primarily based on a probabilistic relationship between conflicts and crashes. And here are our test networks. We have 3 test networks: Manchester, Leicester in UK, and City of Athens in Greece. And we have tested CAV market penetration rate in these test networks varying from 0 to 100% in 20% increments. So let me present the preliminary results from Manchester network. The plot on the left is presents conflicts against fleet composition, and the numbers that you see on the horizontal axis, they correspond to different vehicular types. So the first corresponds to human-driven vehicles, second to first-generation cabs, and third to second-generation cabs. So with 100-0-0 scenario, it means there are 100% human-driven vehicles and no cabs in the network. While with 0-0-100 scenario, it means there are no human-driven and first-generation cabs in the network, and only 100% of the vehicles are second-generation cabs. However, it is also important to note that we have considered both both passenger vehicles and freight vehicles in the network. If you look at the trend of the conflicts, you can see that initially with low market penetration rate, there isn't much change or reduction in conflicts. However, with increase in market penetration rate, there is a gradual decrease in conflicts. And at 100% market penetration rate, there is a significant reduction in conflicts. The plots on the right present crashes against fleet composition, and the crashes are estimated using the proposed methodology, which I talked about in the previous slide. And an important thing to note about these results is that these are network level results. So sorry, these are network level results, and the fleet composition includes both passenger and freight vehicles. And so the trends also include impacts coming from the network characteristics and fleet composition. However, the relative change in conflicts and crashes between different scenarios provide useful insight for analyzing safety impacts. I would also like to mention that the increase in crashes here is primarily contributory to the mixed fleet or the fleet composition that we have, and that is primarily arising from the vehicular interactions because of mixed vehicles in the network. This can also be observed from this normalized plot, where crashes are normalized per number of vehicles. You can see that with the introduction of cabs, starting from first generation to second generation, there is a gradual reduction in number of crashes. These are results from all three networks. These results have been normalized per distance traveled. Since second generation cabs are modeled to maintain shorter time gaps, there is more distance traveled in the network. So these results are more comparable, which are normalized per 1,000 vehicle kilometer. And the first thing to notice is that you can see variation in results between different networks. So there is an impact of network characteristics on the safety impacts or on the results from microsimulation. And as an example, you can see that in 0-0-100 scenario, or with 100% market penetration rate scenario, there is different reduction in different networks. 45.5% reduction in Manchester, 22.3% reduction in Leicester, and 49% reduction in Athens. So the message to take is that the network characteristics, and so the results vary between different networks. So the network characteristics also impact the results. These are the references that we have used. And I would also like to mention that we are in terms of our next steps, we have several sub-use cases within our project, and in next steps we are going to include. We are going to analyze the safety impacts under those sub-use cases. Thank you. That's all from my side. If there are any questions or suggestions, please put them up on Q&A.
Thanks a lot for your presentation, Amna. There are some questions in Q&A, and I would like to take one of them to be answered live. I think the most difficult one to answer as well. It's about the relevance of the result. They depend on the level of the level that the simulation or the model corresponds with reality. I think a very good question. How is that validated? Can you say something about that? Amna?
In my first slide, that are you able to hear me?
The connection is not very good, but please try again. Okay, we don't hear you, Amna. So I suggest to answer it in the chat or in the Q&A. So thank you, and I would like to ask Andreas to share his screen and to start his presentation.
Yes, hello. Let me just quickly share my screen. All right, can you see?
Yes.
Can you see the presentation? Okay. Excellent. So thank you. My name is Andreas Hula. I'm with AIT, the road safety team in the Center for Low Emission Transport. And within Levitate, I'm working on the impact estimates, the estimates for the primary impacts on vulnerable road users through the introduction of autonomous vehicles. So, yes. So I'm interested in unmotorized vulnerable road users, pedestrians and cyclists primarily. Those are not featured in the micro simulation currently, or their interactions would not be very detailed. So we suggested to use current accident statistics to obtain an estimate on the impacts of AVs. Yes, so we used accident data such as the one displayed here, with a list of causes upon registration. And you can see distraction and distraction of the human driver, some driving under influence of substances, and ignoring the priority of pedestrian were major causes for accidents. And these causes should be eliminated by AV systems. AV systems should not be distracted. AV systems should not ignore a red light or a pedestrian crossing. But that would not eliminate all causes. We believe that the share of pedestrian at fault or cyclist at fault could be a proxy for the share of accidents remaining after the introduction of autonomous vehicles. But
Andreas, could I ask you to please start presenting your presentation, because now we see your whole screen.
Oh, okay.
Just try to share it again and then start the presentation.
Oh, okay. Okay, and now. Let me see, it's worked. Ah, yeah, sorry. I will share again. Sorry about that. Yes.
Perfect.
Okay.
Thank you.
Now it should work.
Yes.
Okay. Sorry about that. Let me quickly repeat. So we are talking about unmotorized vulnerable road users, pedestrians and cyclists, and their interactions are not in the current microsimulation models. So we are trying to estimate the impacts via accident statistics and considerations on the reaction time of autonomous vehicles. Yes, here there was a list of accident causes. Most of them should be eliminated by autonomous vehicle systems. But of course, if there's vulnerable road users at fault, if they are crossing very close to an autonomous vehicles or such, or are picked up very late by the sensors, then accidents could still happen. However, these accidents should still be somewhat mitigated if we consider improvements in reaction time of autonomous vehicle systems. To estimate those, say, we have seen from various studies that 30% of accident at fault with a vulnerable road user is a common share, but we plan to make this a variable that this share a variable that the user could specify. Then the question remains how much of that could still be mitigated by AV systems. In order to estimate that, we use a common formula for braking distance. That's if an obstacle is picked up, if another road user is noticed, the vehicle will still drive a certain way, speed times reaction time, and then decelerate. And given the supposed superior reaction time of an autonomous vehicle, we then calculate a kind of equivalent speed. So an AV driving at a certain speed should brake as well as a human driving at a certain lower speed, and then use a relation known as a power model of accident numbers to calculate a reduction, in this case, of accident numbers from the difference between the speeds that the car was actually driving, the AV was actually driving, noted here as V human, and the equivalent speeds that the AV can brake as good as a human driving that speed, which is VAV and which is smaller than V human. So we used parameters in line with what was used in the microsimulation. Between human first and second generation AVs, there's differences in the allowed maximum deceleration and differences in the reaction time. And we then obtain formula, a kind of dose response, yielding a kind of dose response curve based on the share of accidents remaining, which is, we assume the human causes to remain, which is this 0.7 times human drivers, and then the vulnerable road users at fault shared we assume to be reduced based on this reaction time formula. This then yields an impact estimate of the following shape based on the baseline scenario, the gradual introduction of AVs of various generations into the vehicle fleet. And you can see here there's a strong decrease based on these assumptions in the share of accidents remaining compared to human-driven vehicles, as human drivers are replaced by autonomous vehicles. And then there's a smaller decrease from first to second generation AV. Thank you very much. And yeah, I'm happy that this worked now.
Thanks a lot, Andreas. I see there are some questions for you in the chat. Maybe you can have a look at them, or in the Q&A, maybe you can have a look at them after the presentation. Then I would like to end with some concluding remarks. So I'm trying to share my screen. Do you see it now in presentation mode?
Yes.
Okay, perfect. Sorry, I have to at the same time move some other screens to the other. Okay, so some closing remarks. So if we go back to the poll, we can see that from the presentations that you just saw, we can see that CAFs are expected to improve road safety. I think it could be a considerable improvement as well. So if we see that most people expected a considerable improvement, I think that is indeed the answer to the poll. But of course, we don't know yet because the future will tell us. But there are some remarks I would like to make. First of all, even at 100% penetration level, we saw that crashes will still occur. We saw it from the micro simulation, but also in the micro simulation and in the impacts that we are quantifying within Levitate, not all impacts are included. As Rins mentioned, for example, there will be some system failures. There will be some cybersecurity issues. There will be some issues that are not covered in our quantification of impact yet. And there are also groups of crashes that are not impacted by connected and automated vehicles. Like, for example, in the Netherlands, we have quite a lot of bicycle-only crashes, and those crashes cannot be prevented by connected and automated vehicles. So even if the connected and automated vehicles would function perfectly, then still not all crashes can be prevented. And there will also be crashes by unexpected behavior of other road users that cannot be prevented by even perfectly functioning connected and automated vehicles. Second, as we saw from the micro simulation, mixed traffic seems to be a challenge for road safety, as it could be difficult for human drivers to deal with the changed behavior of connected and automated vehicles. So I think that's something to take into account when introducing increasing levels of connected and automated vehicles to the network. Another comment I would like to make is that it's very difficult to quantify the impacts. The future is still unknown. We had to make a lot of assumptions, for example, related to the micro simulation. We had to make assumptions about the behavior of automated vehicles, different generations of automated vehicles. Concerning the vulnerable road users, we also had to make a lot of assumptions. So many assumptions are needed to quantify the impacts. So the impacts are just preliminary impacts, some general estimations, but it's very difficult, and that also relates to the validation question. It's very difficult to really determine what's going to happen in the future. Last but not least, road safety policymakers can influence the impacts of connected and automated vehicles. And that can be done by, for example, if you look at mixed traffic, there could be, for example, dedicated lanes for automated vehicles. There are all kinds of other measures that policymakers can take. And that's also an important aspect of Levitate. That is what we do in the sub-use cases as well. That's something for policymakers to keep in mind. So that were the concluding remarks. I think we have a couple of minutes left for some additional questions. So I'm going to stop sharing my screen so I can see the questions again. How do I stop? Stop sharing. Yes. So thanks a lot for your attention. Let me see at the questions. There is a question about the definition of the first generation vehicle and the second generation vehicle. Anna, I don't know if your connection is good again. Anna, can you hear me?
I don't see Amna anymore in the webinar.
Let me see if I have another question. Yes, maybe that's something Andreas could say something about. I think you already typing an answer, but maybe you can answer it in real life, Andreas. Have there been any indications or exploration of overconfidence in the AVs leading to a more risky, vulnerable road user behavior? Andreas, could you say something about that?
Yes, so we considered this, especially since here in Vienna we had one might say a similar case, in fact, during an experimental AV deployment. But we were unsure how to quantify this, which is always the big challenge for PST integration in this case. So it is mentioned, but we could not give numbers for it.
Okay, thanks a lot, Andreas. I see there are some questions related to the system detections as well. It was mentioned that results from a Slane project found that only 47% of the speed signs were detected by the systems, so a very low rate of detection. Within Levitate, we mentioned that there are some issues also with the identification of signs and with the detection, for example, also of other road users. But we didn't quantify those impacts within the project. That has also to do with the term the time interval we are looking at. We expect the vehicles to improve over time still, and we expect that they will only be really allowed on the road if they function quite well, very well, and they don't they don't have major detection issues anymore. So we decided not to quantify those impacts within the project. Something else that's not quantified within the project is the transition of control. During, like if you have level 3 vehicles, then it's in some cases the human driver needs to take over control. We assumed within the project that the cars are driving fully automatic all the time, and the road users, the human drivers, don't need to take over control anymore. So that are just some basic assumptions in the project. Let me see something else. Yeah, it's a pity that Amna lost connection because most of the questions are from Amna. Let me have a look at the chat as well, if there are some remarks there. I don't see any comments in the chat. So may I suggest to leave it here, or should we leave it at that, or is there another panelist that wants to answer one of the open questions in the chat? Okay, in that case, I would like to thank all of you for attending this webinar. As Balázs mentioned, the webinar is recorded and the recorded webinar will be available on our website. If you would like any additional information about the project, please have a look at our project website or contact us. Thank you very much for your attendance. Bye-bye.